All right. Looks like I did a pretty good job last day. We have a lot of space. I like it. All right. So, how is assignment 0 going? Should be good for you, right? Because you're here still. Okay. Sounds good. How many of you are still auditing? One. Like, you are not officially taking credits, just auditing. One? Just one? Two? Three? All right. That's fine. As long as we have space, I don't mind like people sitting in my class. That's okay. Good. So, we will get into business today. So, we will start with this decision tree thing, right? We talked about it last time. So, let's do some refresher. What is the difference between, yes, a traditional algorithm and a machine learning algorithm? Yes. Sorry. Yeah.
A machine learning algorithm creates algorithms. One algorithm just creates data from data.
Exactly. Exactly. So the output of a machine learning algorithm is another algorithm, right? So what we do for traditional, no, this one is a mess. Let me see. So if we have an algorithm, what we normally do, we input some data, we process it. The process is the algorithm, right? And from the process, we output data. Now, if we know the process, if we know how to process data, then we don't need machine learning, right? Because you only need to learn when you don't know how to process it. So if I know how to process my data, there is nothing to learn. I already know what to do. But if I don't know how this looks like, but I know what is the input, what is the output. I have a black box. I'm giving some input. I'm observing some output. That's where the learning comes. So you observe some black box. You give some input. You get some output. So normally in machine learning we call it X. We call it a Y. Right? The target variable, your input variables. So the input, this is called the input. And this is the target, or the output. Now you have many examples like this, but you don't really know how this Y is generated from X. You don't know the process. You don't know the function that does this. That's what machine learning is about. Right? You are trying to uncover this black box. Now, in the previous class, I said like, we need to make some assumptions when we try to uncover this box. Why? Why do we need to make assumptions? What is wrong if I don't make any assumption here? What is the problem? Go ahead.
So that you will just be getting X
keep getting x and y back? Well, let me rephrase the question. The question is about this box. I'm going to make some assumptions about this box. What is a problem if I don't make that assumption? Yes.
The entire point of the box being there is we don't know the process, so we have to guess that.
If we don't do that, what is a problem? Yes.
I mean, one potential one would be you're searching effectively that function or that algorithm you're looking for. You're searching a massive problem space. You need to constrain it to have a more guided approach to finding the right one.
Exactly. You cannot search through. You cannot even iterate over all the possible functions that you can try. I mean, there is no restricted space. You need to make some assumption that the function, the box, takes some kind of forms, right? And in decision tree, that exactly looks like a tree that looks at this x, and x will have different components. We call them attributes or features, and try to make a decision about y. So we assume that y is generated from x by traversing a tree that makes a decision by looking at the attributes of x. That is the assumption we are making. Okay? All right. So let's go back to this play tennis example. And that is Alex, by the way, my student. Okay? If you haven't met him. So Alex has some way of deciding whether he is going to play tennis or not. So this is Alex's mind. Alex's mind. And obviously we don't know what is going on in his mind, but we can try to infer how he is thinking. Right? How? Because, let's say, I call Alex every day in the afternoon, right? In the evening. And I ask him whether he's going to play tennis today or not. That's my why. Play tennis. Hey Alex, are you going to play tennis today or no? Right? At the same time, I'm assuming that Alex makes this decision based on some weather conditions, right? And then I look at some weather variables at that time. I'm making an assumption that the decision whether Alex is going to play today or not is actually based on some weather features, some attributes of the current weather. But I don't really know like what feature decides what. Like if it is sunny whether Alex is going to play or not, I don't know. But I have this x and y. I call Alex every day, let's say for a year in the evening, and I gather data whether Alex is playing or not today versus the weather condition at that particular moment when I made that call, right? Now I have many different x and y. Now can I make a better prediction? When I say I know that person better, he's gonna do it. Why do we say this? Because we have many data points about that person's behavior. And that's exactly what machine learning is trying to imitate. It's trying to figure out what is that function, and that function takes the form of a tree. We are assuming Alex's brain is framing or constructing it, has already constructed a decision tree. We are just trying to uncover that tree. All right? That's our goal. Okay, so you can see some examples. Like there are 14 days when we made that call and we got this kind of responses. So we assume that this play tennis variable, whether Alex is going to play tennis or not, that's a binary variable, right? You see, this is our target variable. This is often called, this is our y. This is our target. This is our label. You name it. This is our class. Yeah. And now we have a binary variable that we are trying to learn. This concept is a binary variable. Either Alex plays or he doesn't play. And then, based on every day's data, we have some other variables also we are looking into. And we have already made that assumption that Alex makes his decision of playing tennis based on these 4 variables. Is this assumption correct? We never know. Right? I mean, we are assuming this is a reasonable assumption. Alex might be doing this. But you never know for sure unless you hack into Alex's brain and really see what the tree looks like. So a big job in machine learning is to make assumptions in order to make things feasible, because we cannot really hack into Alex's brain, or we cannot really know whether he's simulating a decision tree or like a random forest in his mind or some other way of decision process. We don't really know. But all we have to do is to figure out, like, if we assume that's a tree, that can reasonably correlate with how Alex actually behaves. That's the purpose. So we have taken a lot of data, right? So tell me, based on this, any pattern you see in the data, like when does Alex actually play tennis? What do you think? What can you infer? Yes. When the wind is weak. Okay, let's see. Weak, no. Weak, yes. I see one weak and then there is a yes on the third row. So that's not the only deciding factor. Yes. When Outlook is overcast, Alex is always playing. Yes. That's true. But what if it is not overcast? Sorry?
Normal humidity.
Humidity. Okay, let's see. If it is not overcast and if it is a normal humidity, but here you have a normal humidity, yes, yes, okay, but this is no, right? Normal humidity, but no. So it's not, we have a counter example, right? So now assume that you have millions of data points. Then there is no way you can manually figure this out, right? And that's what the computer can help you with, processing a lot of data. Questions so far? And because we're trying to learn from this data set, it's called a training data set. We are basically training this model using this data, X and Y. And after training, we will get an algorithm, because this tree itself is an algorithm, right? You can create rules from a tree by traversing the tree. It's the knowledge we are going to extract. So tell me, what would be, why not just memorize the entire table? That's our knowledge, right? Is that learning? If I just memorize the whole table, what is wrong with this? Why is not this learning? Yes.
The actual algorithm is much simpler
Exactly. I mean, there is this debate, right? What is memorization versus what is learning? Nobody will agree where the boundary is, but you kind of see those are two different things, right? There is a boundary somewhere in between. If you just memorize everything, that's that's not basically learning. You are not generalizing anything. You need to generalize things. Yes.
I was going to say the data set may not include every possibility.
Exactly. Also, as well, the data set doesn't have all the possibilities. So it may be never possible to generalize in all cases, but we just need to show as humans, we also make mistakes, right? We make wrong predictions. But as long as that is something reasonable, that's useful. That's the point. Okay? All right. So this is what a reasonable tree will look like. Of course, this has already been pre-computed based on this data, but we will go over why this tree is a good tree. But the point is, the whole decision tree, what is a decision tree? First, we need to define that F, the assumptions, we need to make it more concrete. So the decision tree is basically a tree where you first select an attribute from the X, because X has how many attributes here? 4, right? The outlook, the temperature, the humidity, and wind. These are the 4 attributes of X. A tuple consisting of the values of outlook, temperature, humidity, and wind constructs an example, a single X, a training example, right? Now, we need to first, the decision tree, the way it works is you first select one of the attributes from X, and then you make a decision based on the value of that attribute. Now, if it's a tree, tell me what additional assumption I have to make. For a tree, yes. Exactly, that my values are going to be discrete. Okay, what is our discrete variable? What is a continuous variable? That is not discrete, right? And then what is discrete? That is what is not continuous, right? But then what they are? Integer. Finite, exactly. When your set of values are finite, restricted to a finite set of values, that is a discrete value. When they are infinite, that is continuous. For example, real numbers. Versus, well, integers are also infinite if you don't restrict the set. So as long as it is infinite, that is continuous. If it is a finite set, then only. And why is that important? Because you have to decide which route you are going. You cannot have indefinite amount of paths. There has to be a restriction. That's how trees are defined, right? So what is an assumption that we make in decision tree? That the attributes of X, the input data, the features are discrete. Okay? So that is again another assumption of this function, that this function only processes discrete data. Of course, that's a limitation, and we will see how to get over that, but that's right now what we are looking at. Questions? All right. So, and then based on the values, because it's finite, you can choose each path, and based on the path, you take another attribute on the path. You consider the next attribute. But before considering any attribute, you first look at if there is a particular value. Let's say this is a variable x1 which has 4 possible values, a, b, c, and d. Now, if x1 equals to a and your target concept is only yes or no, pure cluster, there is no impurity, there is no confusion. Like if x1 equals to a, let's say every instance within this value, like where the value is a for x1, the label is Alex is going to play tennis. Then do we need to look at other variables? Do we? No. That means we already know. Every time when x1 equals to a, Alex is going to play tennis. Yes. You stop here. So tell me this, if the whole table, this column is always yes, is there anything to learn? No. I mean, yes, I mean, you have already learned that Alex always plays. It doesn't matter. You have learned that x does not matter. You still learn something, but there is no point of learning further. Yes?
So do you choose the highest correlation for your first variable?
Yes. Good question. How do I know which variable to choose first? And that's exactly what we are going to teach, like in this decision tree induction algorithm. That's just coming. All right. Any questions so far? The real question is now, I know I will make decisions, but then in which order the attribute I should consider? What trees? Because if I don't choose x1, I choose x2 first. That's a different tree, right? Then which tree is preferred? And there are, now you can see an infinite number of trees, not infinite, but a huge combination of trees that you can create from this table, right? From the different paths, different values, different variable orders and all that. Still now consider millions of examples with hundreds of attributes. That's still a problem if you go over all the possible trees. You still need to make things more efficient. And these algorithms were proposed in the 90s, where we didn't have the computers that we have today. So they were really into, I need to get this as efficient as possible. Right? So each branch from a node corresponds to one of the possible values. So first of all, you have a node, that is the variable. Each of these branches are values that the variable could take, and based on that, you either make a decision or you recursively choose another attribute and follow the same process until all your examples, until all your nodes, you have reached to the leaf, like where everything is either yes or no. That's the process of decision tree, all right? And then based on, if you are given a new example with these values of outlook, temperature, humidity, and wind, you traverse through the tree until you reach the leaf, then you have a decision. That's your learning. It may not be correct, but at least it makes a prediction. Now the real question is, we know what a tree looks like. The problem is, which tree is the best tree? I mean, obviously you could compute all the possible trees and see which one is more accurate, but that's not feasible. We need something that is more efficient. Okay? So let's formalize with some notations now. Whatever we have talked about. So what we are trying to do, our label training examples are pairs of xi and yi. And we have many such x and y combinations, right? Because we are making call to Alex every day. And then this x is a combination of feature in our case, this is, let's say, 4 features, XA, XB, C, and XD. And we have a target variable, Y, which is either 0 or 1 in this case. Either play or not play. All we are trying to do is to figure out the function that transforms X into Y. That's our problem. So, and now, as we said, like we have many different trees that can explain this data. That basically means we have many possible hypotheses that we can test. Right? Each tree is a possible hypothesis. Maybe not all of them are good. Obviously they are not, but then they are a candidate hypothesis. What we are trying to do is find out the hypothesis that best approximates the target function. So that is consistent with the data. And there are multiple options still possible. Then how do we choose among all these different like variations of the tree? And each variation is actually a hypothesis tree. And we just need to figure out the best tree. And the definition of best is what we are going to talk about. Question? All right. So let's try to, but yeah, we see this is a complex problem, right? I mean, even like when we started guessing what the tree might look like, we already made some mistakes, right? Maybe this is, we said like, if this is true, then probably he's playing, but then we found counter examples. It's not easy when things get larger. So let's start with simple cases. How many of you don't know logical and or? Okay, I don't see any hands. So everybody knows this. So what would be a decision tree for the AND problem? Assume everything is binary variable. Yes, go ahead.
You check X2, it's false or done. If it's true, then you check X5. If that's true, then you return 1. If it's false, then you're also done. You check 0.
Right. Who did not get this? Who are still confused? Nobody? Okay. So what Hugh was saying is basically you look at X2 and you have two possible cases, right? Right? What are the cases? 0 or 1. If X2 is 0, what should be my output? 0. If X2 is 1, what should I do? Check X5. What are the possible values of X5? 1, 0. If this is 1, what is the output? 0? 0. Question. This is the decision tree for an AND problem. Right? Think about the truth table, right? So this is just an alternative representation for the truth table. So 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1. This is the AND truth table, right? Everybody knows that? Truth tables? Okay, tell me what is an alternative tree that also works? Yes?
You can just flip X5 and X2.
Yeah, just swap X5 and X2. Is that a problem? Which one is the best? Sorry? They are equal, okay? Any other logic? Yes. Oh, there is no x3, x2 and x5.
Yeah, so if you have data, right?
Right.
If it filters out more, then I would choose whatever one filters out more data.
Right. If you're curious about efficiency and you care about that, and in your testing data you see many cases of x5 being 0 versus x2 being 0 or 1, then probably like with just one comparison, most of the time you can make a decision if your data is like that. It depends. So the definition of best depends. What is going to be an OR tree? So in case of OR, this is like 0, 1, 1, 1. Then what should the tree look like? Yes.
Basically looks the same, except we're flipping the ones and zeros.
Except for flipping the ones and zeros. Okay, so I'll start with any of them. If it's a 1, you know the output is yes. If it's a 0, you look at x5. Well, in that case, you two have x2 and x5. So let's say x2 and 5, right? So then you look at 0 and 1. You get a 1, that's yes. Otherwise, no, right? Can I flip x1 and x2 and x5 here? Can I or can I not? Yes? No? Yes, right. Okay, and that's your homework, right? How you can do this. What would be the decision tree for that logic? It's a little more complex, right? But you should be able to do it. Questions so far? Good. No questions often means two alternative possibilities, right? One is that we understood everything, and the other option is we don't even know what we don't know. What?
How we are rating this, like x2 and x5 or no, the homework one?
Yeah? These are binary variables. And you just need to construct a decision tree for this logic.
It just has no limitation.
And this is not.
When you have x2 next to x5, does that mean?
This is AND.
Okay.
This is OR. AND. It's a NOT. And three of them are AND. This is the traditional discrete math AND or logic NOT. All right? Questions? Good. Wait, I should be doing presenter view. Yeah. So, now back to our example, where it's not binary anymore. It is still discrete, where the values are fixed. Because binary one, is that a discrete variable or continuous? Discrete, right? Because there are only two choices. It's a finite set. Here you also have fixed number of choices. And you have 4 attributes. And again, we need to figure out which tree is the best tree. In case of AND and OR, that was simple, but then when things get complicated, it's not that simple. And then there, we could just swap x2 and x5, but in this case, probably we cannot. I mean, if we can, but may not be optimal. So we need to be more intelligent. I mean, at least the machine has to be more intelligent, right? So how do we do this? So our computational problem is, how do we automatically find a good hypothesis? That's the computer science problem. Find a good algorithm. It's an algorithmic challenge. And a learning challenge is basically, how do you know that the tree you have learned is actually a good one, that it will actually generalize to unseen data? So if I give you no more unseen data, it will make correct predictions, right? How do you know that? And the second one is the simplest hypothesis is often the best one. That's what we are going to use in order to learn this tree. Because if I can explain something very easily, why make things complicated? If I can make the decision by looking at one variable, why bother about other variables? And the simplest model is often the best model that works well in real life. Not often what you see in academic research papers are the simplest ones. They just want to make it more fancy, right? Otherwise, it's not cool. But when you go to industry, when you go to practice, the simplest ones are always preferred. Right? So, we will try to find a tree that will generalize over unseen data, and that is kind of the simplest tree. And what is the simplest tree? What do you see what do you feel when I say like simplest tree? What is simple? Few nodes, yes. Yeah. I mean the depth, the smaller the depth of the tree. Yes, go ahead. Binary decisions. Yeah. But then if your variables are not binary, then you have to either consider them as it is or you have to convert them to binary. Right? Yes. Any other questions? All right. So we would like to construct a tree that is smallest and still do the trick. Right? Again, if I try to find the smallest decision tree, that is an NP-hard problem that has been proved in 1976. I was not even born at that time. Probably you guys are not as well. But yeah, unlikely to have a poly-time solution, right? So what we are trying to do is to be more practical, apply more heuristic, apply some assumptions, and come up with something called greedy algorithm. How many of you have heard of the term greedy? How many of you have no idea what a greedy algorithm is? Everybody knows what greedy is, right? Kind of. So the idea is you become greedy. Whatever you are getting right now, take it. So you don't know whether it's going to be optimal at the end. Sometimes we make sacrifices now so that our overall, in the long run, we make more profit or progress, right? The greedy algorithm doesn't do that. It takes whatever is optimal for now. You don't care what is coming tomorrow. What is happening next? It's not optimal in that sense, but it is locally optimal. But it simplifies things because you don't need to compute all the possibilities. You just need to compute the possibilities that is happening right now. You don't care about long-term benefit. That is something we are going to do with this heuristic, because even finding the smallest tree is computationally hard. It is going to take an infinite amount of time if we have large number of features, large number of instances and all that. So we are not going to do that. We are going to simplify things. We are going to be greedy and hope that that helps us. So we have already talked about many different assumptions that we are making in this decision tree. Is that clear? So in exams, questions are coming. Decision tree makes the following assumptions: 1, 2, 3, 4. How many of them are true and false? Right? So you really need to understand, or maybe I'm giving you a modified version of a decision tree, a revised algorithm, and ask you, okay, tell me what are the assumptions that are made in this algorithm, learning process. Okay? All right. So what is now the greedy algorithm we are going to talk about. This is the induction process, and the algorithm is simple, just 2 lines. First line, pick the best attribute to split, because you have to pick an attribute and split. Pick the best one, and in the second, if it is pure, then you are done. Based on the split, if your target variable is pure means there is every one of them is either yes or no. You are going to play tennis or no, you just have one option. That means you have reached a pure decision. There is no uncertainty. You are sure that either yes or no is going to happen. There is no confusion. You stop, or if there are still confusion, you just recursively do what you were doing at the child. Simple, right? Pick the attribute, then either stop or keep picking attributes. Questions? Because you have to implement this algorithm in your assignment 1. Okay? Yes?
How do you know where to choose the next attribute? As in, what tier, what side you go with?
Yes. So now the only question is, what is the best? And to do that, we will compute something called information gain. The attribute that gives you the maximum information gain is the best attribute. How many of you have heard about information gain? How many of you have no idea what information gain is? How many of you have heard about entropy? How many of you have no idea what an entropy is? Entropy? No idea? How many of you know the difference between the idea of entropy in physics versus in information theory? Well, the broader concept is same, amount of noise, randomness in your system, but in information theory they compute it in a very particular way that may not be directly like exactly what physics means. And I don't really know exactly what physics means, to be honest, but yeah. All I know is it's entropy dictates the direction of time, it is increasing over time, it's not going to decrease, and it's the unidirectional and all that. Right? But in information theory, that is just amount of chaos, amount of confusion, amount of uncertainty in your data. That is what entropy is. Now, if you reduce your entropy more, you gain more information. That's how it is defined. So they are inversely proportional. So entropy is a bad thing to have in terms of like predicting things, right? You want to predict with certainty. You know that this is correct. You want to make sure you are making a correct prediction. Uncertainty is not a good thing here. So entropy kind of quantifies that uncertainty. And then whatever attribute you pick, if that can help you reduce that uncertainty, that is the best attribute. That is the good attribute. That is helping you reduce uncertainty. That is helping you gain more information about the concept, because that is what probably is which matters the most. Questions? And we will get into entropy right now, but questions so far? No. Good. Yes?
Are all the trees just binary, or can there ever be like 3 decisions?
Always. As long as they're discrete, you are fine, right? All you need is discrete variables and discrete concepts. Yes?
How much leeway do we have to be able to bin continuous variables to turn them into discrete?
So think about a continuous variable, and can you create discrete variable out of them? You can always define some range, right? You can do bucketing, you can do histograms. You can put things into bins. So that's what you have to do in order to apply this. Questions?
Is it not just as simple as going through each attribute and say a set of training data and just seeing how often that one attribute is linked to the outcome. Like overcast, for instance, is always linked to yes. So that's like a 100% attribute. That's always got a link. You can just go down the line for each attribute. Is that not just like the best way to do it every time?
Yes, and that's what kind of we are going to do. So the attribute, so overcast is, first of all, it's not an attribute. It's a value of the attribute outlook. So it's important to recognize the difference. You have some attributes and you have some possible values for each attribute. So overcast is just a value of the variable outlook. The question is not choosing between sunny, overcast, and rain. The question is really choosing between outlook, humidity, wind, and temperature. That's the question. Once you pick the attribute, you kind of branch through all the possible values. That's given. Yes.
So, just for better definition, what do you mean by the best attribute to split in the first part? It's the one that has the most difference, the least difference of what I want to pull off the one that's 100% right all the time, or do I want to pull off the one that needs to be divided up?
Yes. And the answer is none of them. The answer is I'm going to pick something that helps me make a decision, pure decision, more certain decision, that makes me more certain, that reduces uncertainty, that maximizes gain. Let me go over the concept of entropy and then things will be more clear. So we have already seen this, right? But it's a little more detailed in terms of pseudocode. So that 2-line pseudocode we talked about. Now, first of all, still the best is there, and I'll go there. So pick the best attribute. Then number 2, assign A as the decision attribute. So you kind of pick what I think this is not a good one to use. You pick the first attribute, A1. Then for each value, you branch out, create descendant nodes, and at those nodes, for each value, A1, A2, A3, in that node, you again make that same decision process, but just no longer consider this because it is already done. You have already considered this. Keep doing this, right? Then this is the key question that is coming up again and again. And that's where entropy will help. The definition of entropy will help us. So before defining entropy, actually let's first define entropy because that's the amount of chaos. This H variable, so if you have a random variable X, H of X is the entropy associated with X. That's how we represent entropy. And that basically means this random variable. Okay, so first of all, tell me what is a random variable? Is that a variable? Is that even a variable? Yes. It is a distribution, but where does this distribution comes from? Yes. Yeah, what is another name for mapping? Function. Yes. Random variable is not a variable. Your whole life was a lie. Right? It's a function. And the function is probabilistic in nature, random in nature. It is throwing out different outputs. Right? So the random variable, in this case, our target variable, what random variable are we most interested in? The play tennis. Because sometimes it's true, sometimes it's false, it's random. If we are not given any other information, that's completely random to us. But probably given more information, that will become less and less random. That will become more obvious over time. If we understand the relationship between X and Y better. That's the goal of learning. Initially, I don't know whether, will I explain? The answer will be, I don't know. Uncertain. But then I give you the data and I tell you, go through this and probably you know more. You become more certain whether Alex is going to play or not. So you need to quantify what is the uncertainty of this variable and how do you reduce it. That is the whole goal. Right? So, this is the uncertainty originally for your target variable. And this is your uncertainty, conditional uncertainty, given some value of particular attribute. Now, you know A attribute from X. The value of A attribute, you know. Now, your uncertainty, tell me whether it will, what will happen to it? Will it go up, remain the same, go down? You had some uncertainty about this. You were uncertain. Now I tell you one information about X. Is this uncertainty going to go up, remain the same, or going to go down? Can it go up? Okay, you are uncertain about something, and I tell you, I give you some information. Can that increase the uncertainty?
No, because you're subtracting.
Sure, but let's talk logically. I see here, I hear both yes and no. Can that increase the uncertainty, even if it is bad information? Because previously you had no information. How can you increase the uncertainty?
You can be certainly wrong. If you knew that information, you're more certain in a wrong direction.
I think if y is not binary, maybe, but because it's binary, it should be leading towards higher accuracy. More certain.
So let's say I tell you that tonight for dinner, whether you are going to have Italian or not, right? As food. Now I tell you it's going to rain tonight. Now if I tell you it's going to rain tonight, the amount of uncertainty that you will have Italian food, can that uncertainty, can that go up? It cannot. You are just adding information. Adding information cannot increase your uncertainty. It can only remain the same or go down. Because you have already had some uncertainty. Now, given more information, you cannot increase that uncertainty. You can go wrong or you can go right, but that doesn't increase your uncertainty or decrease your uncertainty. You are confused. That's your uncertainty. You don't know what prediction to make. It doesn't mean right or wrong. It just means you are confused between two options. The more confusion, the more uncertainty. Yes?
So, given a set of data, can you already put a number on uncertainty? Like, say the outcome is 1, 25% of the time.
You can.
That should mean the end.
That's what entropy does. Yes. So the question was, can you put a number on uncertainty given some data? And that's exactly what entropy does. It quantifies the amount of uncertainty associated with some data. Okay? And then, if you can quantify, assume for now, you can quantify, then whatever uncertainty you had before, originally, subtract it after knowing the information, what uncertainty you have. If that drastically goes down, that means you are now very certain about things. That means this variable A helps you predict Y. And your information gain becomes higher because if this is lower, the minus becomes higher, the information gain is more. So entropy goes down, uncertainty goes down, gain goes up, you pick that attribute, split on that. Clear? Yes?
A is like a specific value for the attribute you do each value.
It's a particular attribute, it's not a value. And we will show what happens for different values. You need to take an expected value over all the possible values of that particular variable. You need to do an expectation. Yes?
Does the decision tree ever end if their uncertainty is never zero?
It never ends. Very good question. If there are conflicting examples, it never ends. You cannot reach purity? Good question. And we'll see what to do there. Right, good. So this is what entropy looks like. So let me, how much time do we have? Oh, we have time. There it is. Okay. Let's talk about coin toss, right? Coin toss. So in coin toss, it's a binary variable, right? You either get a heads or a tail. So two possible choices. So what entropy is defined for the binary variable is essentially this. Minus P of minus log P of minus minus P of plus log 2 base probability of plus. Yeah. And this is going to define how uncertain your variable is. Why? Let's consider some example. And what is this? P minus probability of tails. P plus probability of heads. Okay? Now, let's consider case number 1.
The equation that you wrote is opposite the equation of the thing. Does not matter. The plus minus.
You mean this term here and this term here?
Yeah, that doesn't matter.
Yeah, it's just a summation, right? It doesn't matter. Right. So, think about a coin where you always, it gives you heads. How much uncertainty is there about this coin? Don't look at there, just look at me. And tell me, if a coin always gives you heads, how uncertain you are about the outcome?
Not at all.
No uncertainty. You are 100% certain every time it's going to come up to be heads. Right? So now, what does that mean? The probability of plus and probability of minus. What is that? Heads? 1. What is this? 0. So now plug in that equation. So minus 0 log 0 plus 1 log 1. What is the outcome? Defining log 0 to be 0, which is undefined. What is the output? So 0 times something is what? 0. Oh, this should be minus. What is log 1? Is 0. So the output is 0, no uncertainty. What if I flip the outcome, like every time tails, what happens? It's the same. When is it maximum?
Zero certainty. When you have a total uncertainty.
When do you have the maximum uncertainty?
When it's 50-50.
When it is 50%, right? You know, 50% of the time it is going to be heads, 50% of the time it is going to be tails. So the probabilities now become minus half log 2 base half minus half log 2 base half. And if you do the math, it will turn out to be what? Now, if I have a coin 60% of the time giving heads and 40% of the time giving tails, what will happen? It will decrease because the amount of uncertainty cannot increase. Amount of success can increase, heads, and this is tail. But the uncertainty decreases because most of the time, now more of the time you see heads. It is less uncertain than 50-50 case. You see the point? If you compute in terms of 60 means what? 3 by 5. 3 by 5. And 2 by 5. That number will be less than 1. And this is exactly how the curve looks like. That is just a heads probability. If it is 50%, you get the maximum, but as you become more certain, both ways you actually become more certain, right? Either it's more heads or it's more tails. So no matter what direction you go, your uncertainty goes down. And at the very end, like 0% or 100%, you have zero uncertainty. That's how the curve of entropy looks like for a coin toss. Questions? Yes?
Are like impurity and uncertainty kind of used interchangeably, or are they two separate things?
Say again?
Impurity and uncertainty are like
Yes, yes. They are kind of like interchangeably being used. So uncertainty, impurity, kind of the same thing we are talking about here. Yes?
Just so I heard you right, that formula is only for coin toss? If the for coin toss, the log 2?
That's true. Think about a cube. How many options you have in a cube? Like a die. If you roll a die, how many options?
6.
You have 6. Then how many probabilities you will have there?
6.
6. Your equation changes. So that is your homework, right? What happens to a die? So as you see, like if you have 14 example, you have 9 positive and 5 negative. Entropy is something like this. Entropy will be 1 if you had 7 and 7. That's the maximum uncertainty. Yes?
When you're doing this for like a feature space, when you're trying to create a tree, do you always treat the data set when you're training it as a population distribution, or do you ever like try to extrapolate to like data beyond what you currently have?
Good question. So the question is, do you just assume that your training data is representative of the real data, or do you actually do more tricks to actually extrapolate to make that more real? Again, both happens, depending on your application, depending on the availability of data and whatnot. Because in extrapolation, you are also making some assumptions and you are adding more noise. So it's not always helpful. Questions? All right. So as you see, we have already talked about this. If it's 50-50, you need, okay. So one point to discuss here is this number, that uncertainty you see. In terms of original, like classical information theory, that is basically the number of bits you need to communicate in order to express that random variable. For example, I'm sending you some information, but if you already know like the information what is coming is going to be always heads, do I even need to send it? No. But let's say 90% of the time it's heads, then 90% of the time I don't need to send anything. Only 10% of the times I will just say no. You save bits by reducing uncertainty. Okay? And in case of a variable that is not just binary, the equation just takes this form, right? Now, instead of 2 options, p plus and minus, now you have all the possible options. For a dice, it would be 6 options. For our outlook variable, it has 3 options, so you have to iterate over 3. So that is like an expected log negative probability, negative log probability. That's how we define entropy, and that quantifies uncertainty associated with a random variable, which is not a variable. And then if all the classes are equally likely, you can prove that, and you have C different classes, the value will be equal to this. So in case of a dice, C is equal to 6, so the value, maximum value will be log 2 base 6. Homework. Okay? So coming back to the gain, the question that Hugh asked, like, is it the value or is it the attribute? That was the attribute, right? Because you have some uncertainty with X, and then you are looking, this is the entropy of X originally. And the entropy of X, given that you know A, that is another attribute. But this attribute has multiple possible values. For example, outlook could be overcast, outlook could be, I forgot what, sunny and all that, right? So you have to account for each possible value of A in order to compute this, and that has to be an expected value, and that is what that is. You basically look at the proportion of instances with that particular value, and you compute the entropy for that subset, and take an expectation over all the possible values. That's how you compute this part, the second part. That's why you see that weighted average. Questions here?
So does this have to do with where you assign the second attribute you choose, like which value of the first attribute is the second attribute?
Right now we are only talking about the first attribute. It happens every time. You just change your state. You are gradually splitting the data set, kind of, into chunks in the tree. You are assigning some instances to some portion of the tree. You are splitting the whole data set into the tree. And then the expected value of the conditional entropy is just a weighted average, but the proportions are coming from the individual values the attribute takes. Right? And this is the gain. And whatever gives you the maximum gain, you just pick that. So here are some examples. So initially, how many options you have to pick from? Initially, you have not constructed the tree. 4 attributes, right? You could pick any of them. So how many information gain you need to compute in the first step? 4. And here are examples for 2, like humidity and wind. Right? So before computing, tell me, what is our target random variable? What is our target random variable? Play tennis. That is the concept we are trying to learn. So how many times you see yes, just forget about the X. Just look at Y and tell me how many times you see yes versus how many times you see no. 9 and 5, right? So what is the entropy of play tennis if I don't give you any other, sorry, I want to say entropy. Play tennis. What is the entropy of this random variable, play tennis, if I don't give you any other information? What is that? Right. So you have 9 over 14 log 2 9 over 14 minus 5 over 14 log 2 5 over 14. Is this clear? You have 2 options, And one option has a probability of 9 by 14 and the other option has a probability of 5 by 14. Right? Which equals to the value of 0.94. And that's what you see in the first term. This is the original. If I don't tell you anything, just give you some data about play tennis. That's how uncertain play tennis is. It's a big uncertainty, right? The maximum value is 1. So there is a huge uncertainty right now. Now, if I pick, let's say, humidity, and I pick the value high versus low, normal, right? I mean, there are two options. Look at humidity. It can only be high or normal. There are two options. So you have two branches. And based on the branch, you now split the data set. The original data set that had 14 examples, that will now be split between these two partitions, right? Sorry, here. That will now be split between these two partitions. For how many cases? You have 5 there in the humidity. How many? 1, 2, 3, 4, 5, 6, 7. Right? So 7 versus 7, right? You also see the example here, 4 and 3 and 6 and 1. So 7 and 7 split. 7 of the attributes, for example, humidity. If you split based on this, you have high, you have normal. So the high one, for this, you take only the, now you split the data set. High is D1, D2, D3, D4, all of them. D1 goes here, D2 goes here, D3, D4. What else? D8 and D12. D8 and D12. And the rest of them, D14 as well, right? Okay, D14. Yeah, the rest of them goes here. Based on humidity, we are making this split. Originally, our uncertainty was this. And now we have to decide what happens to uncertainty here and here. And when we talk about uncertainty here, we need to consider only this set. And when we talk about uncertainty here, we only talk about the rest of the examples. Then we compute the entropy here, we compute the entropy here, we compute their weighted average, the expectation, and then subtract from this value. That's why you see these two cases. And you get a final number. This is your information gain. And between the, if we are to choose between humidity and wind, which one we should pick? Which one? Humidity, right? Because between these two, humidity is giving me more gain. And we will continue about choosing this attribute more in the next lecture. We'll see what happens in the next step and all that. Any questions so far?
How did you calculate the original E equals 0.94? Where'd that come from?
This one.
Yeah.
That is coming from that 9 and 5. You see the E on top. The original play tennis has 9 yes and 5 no. The play tennis attribute without looking at any other attribute. It itself has 9 yes and 5 no. And that's why the original E is, entropy is 0.94 yes.
Why do you need the original entropy if it's constant when you're comparing?
That is constant because, well, you don't really need it, right? I mean, if you look at just the entropy, you could just compare like between them for this particular step. But in the next step, they will change because in the following child. That's why you need them, otherwise no. At a particular level, you don't need. Good? All right. You will see your assignment 1 released probably on Thursday, but see you on Thursday.